what's the value and effectiveness of theory versus engineering, this dichotomy in building good software or hardware systems?
Well, it's good design is both. I guess that's pretty obvious. By engineering, do you mean, reduction to practice of known methods? And then science is the pursuit of discovering things that people don't understand or solving unknown problems.
Definitions are interesting here, but I was thinking more in theory, constructing models that kind of generalize about how things work.
Mm-hmm.
And engineering is like actually building stuff, the pragmatic, like,
Mm-hmm.
okay, we have these nice models, but how do we actually get things to work? Maybe economics is a nice example. Like economists have all these models of how the economy works and how different policies will have an effect. But then there's the actual, okay, let's call it engineering of like
Yeah.
actually
Yeah.
deploying the policies.
So computer design is almost all engineering and reduction to practice of known methods. Now, because of the complexity of the computers we built, you could think we'll just go write some code and then we'll verify it and then we'll put it together. And then you find out that the combination of all that stuff is complicated. And then you have to be inventive to figure out how to do it. Right. So that's definitely happens a lot. And then every so often some big idea happens, but it might be one person.
And that idea is in what, in the space of engineering, or is it in the space of
Well, I'll give you an
ideas?
example. So one of the limits of computer performance is branch prediction. So And there's a whole bunch of ideas about how good you could predict a branch. And people said there's a limit to it. It's an asymptotic curve. And somebody came up with a better way to do branch prediction. It was a lot better. And he published a paper on it. And every computer in the world now uses it. And it was one idea. So the engineers who build branch prediction hardware were happy to drop the one kind of training array and put it in another one.
Mm-hmm.
So it was a real idea.
And branch prediction is one of the key problems underlying all of sort of the lowest level of software. It boils down to branch prediction.
Boils down to uncertainty. Computers are limited by, single thread computers are limited by two things: the predictability of the path of the branches and the predictability of the locality of data. So we have predictors that now predict both of those pretty well.
Yeah.
So memory is, a couple hundred cycles away. Local cache is a couple cycles away. When you're executing fast, virtually all the data has to be in the local cache. So a simple program says, add one to every element in an array. It's really easy to see what the stream of data will be.
Mm-hmm.
But you might have a more complicated program that, says get an element of this array, look at something, make a decision, go get another element. It's kind of random. And you can think that's really unpredictable. And then you make this big predictor that looks at this kind of pattern and you realize, well, if you get this data and this data, then you probably want that one. And if you get this one and this one and this one, you probably want that one.
And is that theory or is that engineering? Like the paper that was written, was it
Well, that was probably
asymptotic kind of discussion, or is it more like here's a hack that works well?
It's a little bit of both. Like there's information theory in it, I think, somewhere.
Okay, so
And
it's actually trying to prove some
yeah, but
kind of
once
stuff.
once you know the method, implementing it is an engineering problem. Now there's a flip side of this, which is in a big design team, what percentage of people think their their plan or their life's work is engineering versus design inventing things? So lots of companies will reward you for filing patents.
Yes.
Many big companies get stuck because to get promoted, you have to come up with something new. And then what happens is everybody's trying to do some random new thing, 99% of which doesn't matter. And the basics get neglected. Or there's a dichotomy. They think like the cell library and the basic CAD tools, or basic, software validation methods. That's simple stuff. They want to work on the exciting stuff. And then they spend lots of time trying to figure out how to patent something. And that's mostly useless.
But the breakthroughs are on the simple stuff.
No, you have to do the simple stuff really well. If you're building a building out of bricks, you want great bricks. So you go to two places that sell bricks. So one guy says, yeah, they're over there in an ugly pile. And the other guy is like lovingly tells you about the 50 kinds of bricks and how hard they are and how beautiful they are and square they are and which one are you going to buy bricks from? Which is going to make a better house?
So you're talking about the craftsman, the person who understands bricks, who loves bricks, who loves the
Yeah, that's
varieties.
a good word. Good engineering is great craftsmanship. And when you start thinking engineering is about invention, and you
Ah,
set up a system that rewards invention, the craftsmanship gets neglected.
okay, so maybe one perspective is the theory, the science overemphasizes invention, and engineering emphasizes craftsmanship, and therefore, like, so if you, it doesn't matter what you do, theory
Well,
or
everybody
engineering.
does. Like read the tech rags; they're always talking about some breakthrough or
Yeah.
innovation, and everybody thinks that's the most important thing. But the number of innovative ideas is actually relatively low. We need them, right? And innovation creates a whole new opportunity. Like when some guy invented the internet, right? Like that was a big thing. The million people that wrote software against that were mostly doing engineering software writing. So the elaboration of that idea was huge.